Now I'm going to introduce Tom Concannon, and give me a second to bring up his bio. He received his PhD in semi-classical gravity on the thermodynamics of rotating black holes. Following professorships at both Wake Forest University and Elon College, am I pronouncing that right? Now Elon University, he decided to try software engineering as a challenge. After many years in this industry, he again went to graduate school at Lehigh University to earn his master's degree in mathematics, which enabled him to return to full-time teaching at King's College in Wilkes-Barre. He currently teaches courses on differential equations, mathematical methods in the physical sciences, and computer programming. He strongly believes that learning can only truly be accomplished and appreciated if it is taught to others. So please help me welcome him while I flip out our slides.
All right, thank you, Jason. And thank you, everybody, for coming to this talk. I know it can be intimidating. So as a result, I'd like to introduce you to a famous character in the study of infinity, Buzz Lightyear. In case you haven't seen Toy Story, maybe you should go out and see it. Toy Story 4 is currently playing out in the movie theaters. But it's a good series. I have a 10-year-old daughter, and she loves Toy Story, so I figured I'd give this a little bit of a try. So today, I'm going to talk a little bit about infinity and the concept of infinity. As you heard Jason talk about, my expertise does not lie in the subject of mathematical infinity or anything like that. My expertise lies in relativity, black hole physics, and so forth. But I love math. That was my PhD thesis, was all basically differential geometry and math. And as a result, I like to study lots of weird stuff in math. And because I feel like you should learn too what I just find very pleasing and exciting, that's why you're here, right? To learn a little bit more. So thanks again, and let's get started with this. So Buzz Lightyear's catchphrase is to infinity and beyond. Well, that's interesting. How did you get beyond infinity? That's a weird thing, weird concept if you think about it. What's infinity to you, right? So, all right. Well, one of the famous quotes out there you probably didn't hear of, but when you start studying weird stuff like this, you get all kinds of strange quotes from anonymous schoolboys, mathematicians, and other people that really don't like infinity or math sometimes. But infinity is where things happen that don't. My daughter looked at that quote and said, "Boy, that's terrible. I don't understand it." Well, neither do I, but that's the point. Okay? So, all right. So she wanted to do a quote on her own. She read the Phantom Tollbooth. She did this quote in lots of different fonts because she finds it very interesting to have lots of different fonts in here and didn't want me to change a thing. She's 10, so this was her first time editing a PowerPoint presentation. There you go. So, the Phantom Tollbooth is a strange book, but it does have a lot of mathematical references in it. For example, Milo is one of the main characters in the Phantom Tollbooth, and he was talking to a child while going up lots of stairs to infinity, essentially. The child was part of a 2.58 average family. The child was 0.58 of a child. And so this child was talking to Milo about how that's possible. And Milo basically told him, well, that could never be. And I'm trying to find the laser pointer here now, see if I can do this right. Oh, yeah. But that can never be. Because this laser pointer sometimes doesn't work, apparently. Oh, there it is. Okay, so you got it. Oh, what? Oh, it doesn't show on the screen. That's interesting. Okay, we won't use the laser pointer. But it says, but that can never be, Milo said, jumping to his feet. Don't be too sure, said the child patiently. For one of the nicest things about mathematics, or anything else that you might care to learn, is that many of the things that can never be often are. You see, he went on, it's very much like you trying to reach infinity. You know that it's there, but you just don't know where. But just because you can never reach it doesn't mean that it's not worth looking for. I find that pretty deep for a children's book, but that's pretty interesting because when you try to look for infinity, it's there, but you can never reach it. It's interesting, we'll talk about this. Now, before I get really into this presentation, there will be mathematics in this presentation. Don't be too scared, I'm not going to give you a quiz. Although if you were my student, I would. But don't be scared yet. But there will be a little bit of mathematics in there. I'll gloss over it just to give you a taste of how mathematicians deal with it. Before we deal with that, though, let's just talk about a little basic math. I think we all can count. I'm not sure we all can, but most of us in this room probably can. And we learn counting very young. But how? By counting our fingers and, of course, watching Sesame Street. But when we count our fingers and then try to figure out how many people are in this audience, we start counting the people in the audience. Sometimes people still count with their fingers as they go through. Mainly little children, but you get used to the concept. So it really is as easy as 1, 2, 3, like the count says in Sesame Street. You learn there in Sesame Street the skills you have later on in life, okay? Well, these are called counting numbers. So after 10, of course, unfortunately, we run out of fingers. What did we do next? Well, of course, we have 20 little digits, including our toes, right? So not too many people want to take off their shoes and count their toes while they're trying to figure out if there are 20 people in the room or not. But, you can read little books on this to your, young daughter and so forth, or young children. 10 fingers and 10 little toes. But what happens when you need more than 20 objects to count? Well, we invent these abstract objects called counting numbers, or as somebody we'll meet later named Cantor called them, cardinal numbers. They measure the size of the things we're counting. Not necessarily in order, but the size of the people in the room here, or something like that. Okay? So we'll come back to this cardinal numbers a little bit later. But once we have this concept of number, we can do all kinds of cool stuff with it, like arithmetic. Woohoo, arithmetic. We all know how to do that. I think it's fun. So how many counting numbers are there? There's always, unfortunately, a next number. You know that. You've been in competitions like this, I'm sure. I have 4 apples. Oh, yeah? Well, I have 5. And then it goes on from there. Until, of course, now children say, well, I have infinity apples. Beat that. And if you're a smart mathematician and you know a little bit after this talk, you'll know a little bit more, you can beat that. So you'll see how. That's the challenge today. How to beat that child who says, I have an infinity number of apples. All right? So how do we do that? Well, counting numbers count everything. All the way up to this symbol here, a lemon skate it's called, introduced by John Wallis in 1655. But basically trying to figure out, well, that's a symbol for infinity. Okay? So he invented this kind of number in his mathematical papers at the time and did things like, strange things like, 1 divided by infinity, he meant to be 0. So we hear about this a lot in informal mathematics. 1 divided by infinity is like 0, and so forth. But it does solve the problem of how many numbers there are. Unfortunately, not really a number. That's the problem. More of a concept. Okay? Just because you can never, ever get there. So, that's already starting to go, well, okay, that's really weird. Infinity plus 1. Interesting. So, if I had to ask you guys, have you ever thought about infinity? Yeah? What are your ideas about infinity? What are your ideas?
It's out there.
It's out there. It's beyond, right? What else? Anybody else have an idea, a concept, like a visceral feel for infinity? You go next. It's what we can't know. Okay.
I have a lot to learn, but to me, infinity is mostly a word.
Okay. That's good. Infinity is a word.
One of the questions is, how many dimensions can you have for infinity? So we have this linear dimension.
Mm-hmm.
We have that dimension is perpendicular to that.
Okay.
And the question is, do you have more countable numbers?
Ooh, that's an interesting term. You thought about this a little bit before. Yeah.
Yeah, well, I'm married.
Oh, there you go. There you go. Yeah. It rubs off, right? Anybody else have a good idea about infinity? Yeah? It's endless. Endless. I'll talk about that concept a little bit. That's like eternity, right? Eternity is temporal infinity, as we call it. Okay? Well, that's good. Everybody has at least thought about this before because it does come up occasionally. What is infinity? Most people have thought about this in the modern world. Well, in antiquity, they also thought about infinity quite a bit. And the Greeks thought about it a lot. They were the first to generalize counting in general. But they were afraid of infinity, essentially. So they called it Hare infinity. They were masters of geometry. You've heard of the Greek geometry. Euclid, right? Who had all those theories and proofs about geometry and so forth. The elements. Well, they didn't really master algebra so much. They had a difficult time with that. And as a result, they couldn't intellectually really accept this idea of infinity so much. And in fact, one of the ancient Greeks, Zeno. How many people have heard of Zeno besides the mathematician in the audience? Zeno, yeah. So some people have heard of Zeno. Attempted to show that infinity was not a viable concept. Because if you accepted this concept, motion would be impossible. And of course, we know that's not impossible. How did he do that? Well, there's this, I guess, analogy or some kind of example he used called the tortoise and the hare. Anybody hear about this? I don't like the tortoise and the hare per se. I'd like to use something a little bit more modern. It's from an older movie, though, but it's Achilles and the tortoise. And yes, Brad Pitt there as Achilles. It looks like he's trying to slay the tortoise for dinner, but he's not. I think it's just a cut out there, but I thought it was pretty cool. He starts running. So let's say this race here is 100 meters long. The tortoise gets a head start at 50 meters before Achilles gets started. By the time Achilles gets to 50, the tortoise, say, moves 1 meter. Just giving him a random speed, but the tortoise is slower than Achilles by a lot. Well, once Achilles gets to 51 meters, the tortoise will now have moved a little bit more, say a half a meter or something like that, or a little bit less, I guess, in this case. But in this case, this continues on. As Achilles tries to capture the tortoise moves a little bit further. And so Achilles never overtakes the tortoise. That was his example. And Achilles, of course, came out and said, "You're an idiot. Watch." And he went right past the tortoise. So what's going on here? Well, Zeno said, well, in this case, because this takes an infinite amount of time. If you go halfway, then halfway, and then halfway, and halfway, that infinity can't exist. So what did they do? It seemed like it should exist, right? But in some way, maybe not. So what they did was they invented something. Aristotle saved the day, as he did, for the most part, for a lot of other things as well. He introduced potential versus actual infinity. Now, counting is potentially infinite because the counter stops after some finite time. Potentially infinite. But actual infinity is contradictory because, well, of course, mathematicians did not use it. Paradoxes would not exist. Right? So, actual infinity does not exist. Well, they ran with this idea of potential infinity, basically what mathematicians might use today, if you want to call it that. And so they went, without having a precise definition of infinity, to do lots of cool things with math, even in geometry. So Archimedes, of course, you guys know Archimedes? Anybody know what Archimedes is famous for? The screw, the lever, that kind of stuff, right? Give me a lever of long enough length, I can move the world and so forth, right? He found that if he drew circles in polygons, he could calculate pi. Everybody know what pi is? Pi is the ratio of the circumference to the diameter of a circle. Well, back then they didn't have calculators per se. They couldn't just measure it and so forth and do kinds of calculations in there. They would inscribe polynomials, which they knew the area of both inside and outside, and try to come up upon some kind of limit between, say, what it would be inscribed and outside the circle. And they came up with these really, I guess, accurate values of pi, which is really cool. So, as a matter of fact, he had to do this by hand. I just want to point out he did 96 sides for a polygon, which took him 2 years to do. Calculate the area of a 96-sided polygon. So imagine that could be your job. Calculate a polygon area by hand for 2 years. I wonder if he got paid. I kind of doubt that. But. All right. Well, infinity survives in art. And artists have a good time with it, too. The master of infinite artistry was Escher. How many people have Escher in their house right now? I have it, but they're not on my walls. But Fantastic artist, right? But he was really the unsurpassed master of infinity, as you can tell from something like this, the never-ending waterfall, right, in the river. It never ends, because you really can't, it's just the way he drew the pictures, right? It looked kind of like, well, paradoxical. And hands drawing themselves, right? As well as this interesting picture here that goes to infinity at the edge of the circle. In mathematics, this is called the projective plane, by the way. And he did actually talk to mathematicians and draw what they said to draw, because he could. But he drew so many other interesting mathematical paintings or drawings, you should go check them out. Just type in Escher, and you'll find him. Every single one has been scanned online. Okay? Interesting enough. Well, of course, you guys have heard about this as well. Fractals. That fractal right there, oh, by the way, a fractal is a self-similar object, which means, that's kind of a technical term, but means that it's basically the same object or a very similar object the further you go into it, essentially. It reproduces itself. Okay? This is a famous example of a fractal here called a Mandelbrot set, after Benoit Mandelbrot. And it looks like a bug, but it turns out that if you zoom in, look here, there's another shape right there that looks exactly like that bug. Right? And if you go, oh, there's one on the very end there too. I know you can't see it from way back there, but if you look at this closely, you can see that self-similar nature. Trees have this, right? Go up a tree and there's a trunk, there's a branch that kind of looks like the trunk with other twigs on it. And the twigs have their trunks and so forth. So I'm not going to get into the mathematics of fractals, but just to demonstrate a little bit about why kind of interesting, we don't need the idea of precisely infinity, but in some sense, this comes out. Infinity comes out in this. So I have a couple of interesting GIFs that you can zoom in and see things, how they're like this. I wonder if that worked. Oops, that didn't work. Okay, that one's a little bit better now. So you can zoom in a fractal and see the self-similar nature of it. And the further you go in, the more patterns you see, the more structure you see, and the more familiar it looks from where we were before, which is very fascinating to me. That one doesn't work. I don't know why that one doesn't work, but that was cool because it zoomed out from one section right here in the Mandelbrot set and zoomed in so far, it comes up with the exact same set right there. Now, you may ask me, what's that set really represent? Well, it's just a little bit of analysis there, but a little bit of what numbers converge for a particular equation. Okay, but that's it. But you can generate fractals on your own on the computer if you want. Just go look on some code online or something like that. Well, infinity is also encountered in physics, believe it or not. Something I'm more familiar with. They don't get bogged down in that precision either. Why would you want to do that? Inside the center of a black hole is something called the singularity. Now, a black hole, the body of a black hole consists of a simple black hole here, the event horizon. That's the horizon. That's the point where if you cross it, you never come back. Okay? That's not what we're talking about. The anatomy of a black hole is the event horizon plus the singularity. Okay? And the singularity is a point of infinite density, as far as we know, but not mass. A black hole can have a finite mass, like the mass of the sun, but it has infinite density at that point. And we say infinite as a physicist, we don't mean that precisely as mathematics, because we don't know really what's going on at the quantum level at the singularity of a black hole. It's pretty high density, or that's what we know. Okay? But how do we get rid of infinities? It turns out that gravity and quantum mechanics can't be united. Okay, that's one of the holy grails of physics right now. And because it can't be united, physicists use these weird things called renormalization techniques. Wow, what's that? That's just a way of getting rid of infinities. And it's so weird that physicists subtract infinity from infinity and get exactly the right number to 15 decimal places that we see in experiments. How freaky is that? It's so freaky that I always call it, to my students, magic or just black magic. Some physicists actually think renormalization techniques are black magic. But it is one of our most precisely measured theories in all of nature right now. Quantum electrodynamics. But, well, it turns out that any psychologist in the room, you use infinity too. I mean, you may not realize it. This is the concept of the homunculus. They use this to model subjective consciousness in the mind-body problem. In fact, we have a person here looking in the mirror. Who is the internal observer in your mind? Who is that? Is it you? Or is it a tiny version of you? And if it's a tiny version of you called the homunculus, who's been thinking for the homunculus? Is the homunculus? Or something like that? So where's all the neural processing take place? Either the homunculus or eliminate this internal observer just to lead to an observer with an observer with an observer kind of thing. So it's kind of weird. I don't really get it. Well, wait a minute. I do get it because I've seen a movie called Inside Out. How many people have seen Inside Out? Disney. Oh, come on, people. You haven't seen Inside Out? Really? Really good movie. Like Toy Story, you should go see Inside Out, okay? See, I know all these because I have all these movies for my daughter. But it's a really funny movie. It's fun because we have this little girl named Riley Anderson, and inside of Riley Anderson's head are emotions that are depicted as small little creatures. There's fear, there's disgust, there's joy, there's sadness, and there's anger. And they, of course, control Riley's life, essentially, by, emotional responses. When I was watching this movie, I kept thinking, wait a minute. What if she's sad? How does Joy get sad? Well, obviously, she's got some little characters inside her brain, too. Well, how does that Joy get sad? Or experience any other emotion? Or whatever. And we can keep going and keep going and keep going. Look at that. Look, I got that in PowerPoint. That's pretty cool. That was really hard to draw, by the way. But it was fun. So next time, if you ever go see Inside Out, it's a fun movie, but think about that infinite regression problem as you watch it. All right. So, well, of course, as you know, religion also has a concept of infinity, usually embodied by the concept of a heavenly Father, God, or Buddha, or whatever like that. I guess Buddha's not really infinite, but theologians have abstracted away any notion of gods into a theologically infinite being, meaning that it's omniscient, omnipotent, and omnipresent. Omniscient means all-knowing. Omnipotent is all-powerful. Omnipresent means everywhere kind of thing. Everywhere in the universe. Everywhere beyond the universe, too. So that nothing you can say will change their mind about this, despite its internal paradoxes. The afterlife is described as eternal. Forever and ever and ever and ever. Without end. Amen. Philosophers question these religious cosmological arguments, things by saying, well, then who made the maker? Right? And so forth. So these kind of go all the way down. Infinite regression of makers. So maybe Kyle can talk about that when he comes a little bit. At least mention it. Kyle has a really good paper on the cosmological argument. You should go read. It was very well done. But it's turtles all the way down, says Stephen Hawking, in a very popular book called Brief History of Time. Turtles all the way down. All right. So infinity does appear in our daily lives, even though we may not recognize it. Mathematicians, however, have a little bit more fun with it. And this is where it gets interesting. We need to make infinity precise. Why? Because mathematicians have to work with it. Okay? Infinity celebrated its greatest triumph since Greece, taking the form of infinitesimal quantities in the invention of calculus. It turns out that, I just read a study recently that said that students have a problem going from, say, middle school math, maybe algebra, trigonometry, and so forth, to calculus. And it's not because of calculus is so difficult per se, it's because they think calculus has this concept of infinity that some students' minds can't relate to very well. Infinitesimal is a very small infinite quantity, but as you may or may not know, calculus was invented by Isaac Newton. And he also did physics too, of course. But he was doing science and he said, I need more math. So he just invented calculus. Yeah, part of a side job, or something like that. And he did have some competition, though. Gottfried Leibniz was also an inventor of calculus. Fortunately for us, we follow Leibniz's conventions when we talk about calculus. Otherwise, we'd be talking about fluxons and other weird things that you never heard of, because Newton had some really strange symbology. Okay? But they did things like this, where they calculate, say, the area under that curve there. So how do you do that? You calculate the area under the curve by calculating the area of all these rectangles. And then you take a limit, which I circle down here. You take a limit as the width of these rectangles goes to 0. And it turns out that's called an integration. That sum becomes an integral right here. Now, don't be scared. I'm just going to talk about this. But that gives you the precise value for the area. That's pretty cool. So this is used all over the world now. This helps us out everywhere, from your phones especially and all your computers. Without calculus, computers wouldn't exist, or television, or anything else that we use and love. Okay? Well, but here's a weird situation that was encountered way back when Newton was still alive, I believe. They wanted to find the surface area and the volume of surface of revolution. Okay, so what this means is you take a graph, and we're going to take this curve, and this curve kind of goes like this. And all we want to do is we want to revolve it around the x-axis like this. Okay, we just want to revolve this line around the x. So it looks like this when you're done with it. It turns out this surface of revolution has a name. It's from the Bible. It's called Gabriel's horn. And they named it so because, now I'm going to show you mathematics. Don't be scared. But I'm going to actually calculate the surface area of this. Ready? Okay. As you calculate the surface area from 1 all the way to infinity, because 1 over x never ends, essentially, you get infinity. That area of the surface here goes to infinity. Here's the weird thing. The volume of this horn is finite. In fact, it's pi. So you can have 3.141592653588793 gallons of paint, fill up that horn with it, but you can never cover the outside of that horn with any finite amount of paint. Well, this is what gets you interested in infinity, doesn't it? You're like, what the? How is that even possible? So then you dig a little bit deeper, and then you end up in an insane asylum. Well, I'll talk about that later. So anyway, and now Buzz comes in because he's been watching this somewhere in the back, and he has a comment. That's pretty odd. That is odd. I agree. Well, David Hilbert was a mathematician at the turn of the century, the 20th century, that is, and he decided he used infinity as well. So he basically founded his own hotel. In this hotel, however, there are an infinite number of rooms. They're arranged in a linear fashion from one Telegraph Avenue to forever. And all of the rooms somehow are full of guests. Well, he has a problem now because one other guest arrived. Someone arrived wanting a room. Well, no problem. Hilbert just said, okay, everybody, from 1, you go to 2. From 2, you go to 3. From 3, you go to 4. And so on. And he was able to fit somebody else in the room. This paradox, strangely enough, gets even worse. You can find all kinds of crazy Hilbert hotels online. You can have a busload of people come, and they still find rooms. You can have an infinite number of people come, and they still find rooms. You can have Hilbert hotels that have infinite stories. Oh, it just gets crazier and crazier. I'll just leave you with this. The weird thing is, how do you fit another person in a room that already has full occupancy? That's really strange to me. All right. But this is saying there's a little mathematical expression here. If you want to think about it, infinity plus 1 is just infinity. So when your little child is trying to argue with you about I've got infinity number of apples, and another little child says, I've got infinity plus 1, you immediately correct them and say, that's still infinity, rat. Can't get away with that argument anymore, can you? I wouldn't say Brad. I'd say something else. All right. Oh, whoa, that is weird. That's weird. Here's another one that's really strange. You guys know if you have what's called an N ball. So a 1 ball is just a line. A 2 ball essentially is a disc. Okay. A 3 ball is just an ordinary ball that you can bounce around and play tennis with or whatever. It's solid though. But you can have balls in higher dimensions. And there's formulas for calculating these volumes. So you can calculate all these numbers from integral formulas and so forth. But what's really weird is that as you continue going with the number of dimensions, as the number of dimensions approaches infinity, the volume approaches 0. That's really strange to me, I think. So you can graph the number of the volume, starting out with n equals 1, and it maximizes itself around 5 or 6, somewhere around there. That dimension sphere, ball if you want to call it that, has the largest volume. After that, it goes down to almost 0. At infinity, it's 0. The volume of an infinite dimensional sphere is 0. How is that possible? Let's think about that. No, wait. Maybe you shouldn't. Just be careful. So now he's calling in his friend Woody. If you haven't seen Toy Story, Woody's his best friend, a cowboy toy. So he's calling Woody to come out and check it out. All right. Speaking of balls, I cannot not mention this paradox. This is one that is so weird, it's even used in some far-out physics theories. It's called the Bana-Karski theory. Basically, it's possible to break up a solid ball into finitely many pieces, reassemble them to form 2 solid balls of the exact same volume as the first. Okay? In other words, it looks like this. You have 1 ball here, solid, break it up into some pieces, it's possible to do this, and you form 2 solid balls over here of the exact same volume. Now, of course, this doesn't happen in the real world. Otherwise, maybe the universe would be full of just balls or something. I don't know. But this doesn't happen in the real world. This is a mathematical situation here. So this is just math. It has something to do with the infinity of real numbers. But we'll talk about that in a minute. But because of this theorem, some physicists have contemplated that maybe, when particles decay, maybe that's where some of this comes from. I don't really buy into that theory too much, but it's interesting nonetheless. See, right, that's never going to happen. However, there is actually an interesting consequence. There's a whole book dedicated to the Banach-Tarski theorem called The P and the Sun. It's a little heavy mathematically toward the end, but overall you can say you can have a little P, break it up into some finite pieces, and reassemble it to form the sun. So here's a P drawn to scale, hopefully large P when you're on the screen up here, but the sun is definitely not drawn to scale. Isn't that strange? Another one of those weird paradoxes of infinity. So, by now, Buzz is, that's it. You're a sad little man. Get out of here. We have no more use for you. All right. Now let's get into a little bit of math. I think you guys can all handle this. Okay? Let's express 1/9 in decimal form. You put it in your calculator, 1 divided by 9. And you get 0.11111 all the way out to infinity, essentially. Well, let's do that for 2/9. You get 0.222222, and so on. What do you think we get for 3/9? 0.33333, which is 1/3, right? What do you think we get for 4/9? Just guess. What? 4, right. And so forth, right? So you can get 2/3 is 6/9, which is 0.66666666, and so forth. And 7/8, 8/9. Well, what about 9/9? What's that? No, it's 0.99999999999. Oh yes, but that's also equal to 1. Isn't that interesting? So this number here that you see an infinite decimal representation of 0.99999 is exactly equal to 1. There's actually a really nifty, cute little trick that I asked my students to do a proof for this. It's really nice. If anybody wants to see it, you can. I have nothing to write on, but you can talk to me later if you want. So Yeah, Buzz, I know. It's okay. Calm down. But yeah, there's a nice little elementary proof for this. I'll show you later if you want. All right. Well, that's not the worst thing here that can happen. One of the worst things is that you can keep going here. It turns out that there are like these sums. We're summing fractions up, okay? And if these fractions get smaller and smaller and smaller and smaller, then it is said to converge. It can converge, okay? So we can actually solve Zeno's paradox by this method of converging of an infinite series of fractions, an infinite sum. So if you move halfway across the room, there's halfway across the room. Then you go another half across the room, and then another half, and another half, and you keep going. But when you sum that up, you've gone across the entire room. And if you assume the time it takes you is, say, maybe a half a second, a quarter second, an eighth of a second, then you moved across the room in a finite amount of time, too. So we've kind of solved Zeno's paradox with the aid of calculus, which is really fascinating. So we can solve this. That's a necessary condition. Means that has to happen. If it doesn't happen, it will never converge. If these things keep getting larger, obviously it won't converge, right? Right. Zerg. So I brought that in because most of the students I would give this presentation to understand who Zerg is. Who's Zerg, Matt? The bad guy in Toy Story. Right. Matt's one of my ex-colleagues here, so to give me support. All right. Well, we have certain series like this, though. These terms keep getting smaller. This one's called the harmonic series, but who cares? But we have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, all the way down to 1 over the largest number you can think of, and keeps going. This one, unfortunately, is a divergent sum. You guys know what divergence means? It means that that sum will never converge. It's weird, okay? It diverges. So this is a necessary condition, but not sufficient. So it can happen, but, it will diverge. Weirdly enough, if you square each one of these in the denominator, like 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and add all those up, you do get a convergent number. You get what Euler showed, pi squared over 6. Pi came along in a weird way. Okay, that's interesting. All right, so what do you see? Buzz left. He was so disappointed by all this math, he just left. Woody's over there going, what's going on, man? I thought you said come here. All right. Well, let's talk about infinite sums. I told you there was going to be a little math in here, didn't I? We all know that 1 minus 2 plus 3 is equal to 1 plus 3 minus 2. Obviously, no problem with that. How many have seen those viral math things that are online with 8 divided by 2 times quantity 2 plus 2 and all that kind of weird stuff? You guys surf the web a lot like I do? No? There's these strange viral math problems that come out every now and then. Ignore them. They're for people who do not understand math, including the people who write them do not understand math. No mathematician would ever write these expressions, ever. However, in other words, if we have a sum like this, well, all we do is change the order of the terms around and everything's hunky-dory. Everything we can do, no problem. You can change any convergent sum into a divergent sum or vice versa. Oh, well, not really, but where did I write that from? Anyway, ignore that. But let's consider the harmonic series. Now watch this. If we put alternating signs in, like 1 minus 1/2 plus 1/4 minus, and so forth, right? Like this, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. I color these. You may not be able to see all the colors really well, but it's known to converge to log 2. It's just its natural log. It's some finite number, in other words. Well, this is weird. Watch this. I'm going to do some elementary math for every term. I'm going to multiply that whole series by 2. I multiply both sides by, 1/2. 1/2 times 1 is 1/2. Minus 1/2 is minus 1/4. 1/3 times 1/2 is plus 1/6, and so forth. So I have to multiply the right-hand side by 1/2, and I get 1/2 log 2. Right? Now watch this. Some weird magic happens. I'm going to now subtract these. I'm going to add these two equations together because that minus 1/2 will cancel out with that 1/2. that 1 minus 1/4 will add to that minus 1/4 to give minus 1/2, and so forth. Oh, wait, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. It's not the same as what we had originally, but when we add these two terms, we get 3/2 that constant. But it's the exact same sum. How is that possible? It turns out for divergent sums or sums that are alternating a sign, you can change them to be whatever you want by some deft manipulation of signs. These kind of things are called conditionally convergent sums. So, another weird symptom of infinity. What's going on? Well, don't worry. You're sitting there thinking, oh, well, you know, I might not be able to understand some of these paradoxes. You can if you just study calculus. But it gets even worse. Right, John? It's even worse. Watch this. Oh, yeah, Zurich is definitely taking control of whoever's presenting this. Trust me. It gets much worse. Now, let's add up all the positive integers, counting numbers. 1 plus 2 plus 3 plus 4 plus 5. What do you think that sums up to? Anybody? Infinity? Sound right, right? They keep getting larger, right? Well, that sounds reasonable, but infinity is not reasonable. Turns out that Euler found that you can associate the sum of all the natural numbers with another number. That's not infinity. It's minus 1/12. Go ahead, you can say it. WTF? And there's proofs on this online. So there's this video on YouTube by Numberphil you can look at, and they prove it. Of course, I put proof in quotation marks because it's not really true. However, there is a way that you can associate that sum with minus 1/12. In fact, physicists have done this in string theory. You guys have heard of weird things like string theory, right, in physics? They've done this in something called bosonic string theory. And it turns out that this sum, being associated with minus 1/12, is the only way to get a consistent theory that doesn't diverge. And it only works in 26 dimensions. Fortunately, we don't do bosonic string theory anymore. We do superstring theory, which is supersymmetric instead of bosonic only. We talk about bosons and fermions. But if you doubt me, yes, my mind has been melted, Buzz. Okay, goodbye. But if you doubt me, you just look at the proof. But I even have the book that shows where this is done. I copied the page of the book. It's only on page 22 of the string theory book. But you can actually see it if you look closer. It's right there. N equals 1 to infinity. That's a summation sign, that big sigma thing there. Of 1 plus 2 plus 3 is not equal to, but can be associated with minus 1/12. And he uses that later on in the calculations. So, you know, this is why some physicists even think that string theory is a bunch of, baloney. But that's not the weird thing about string theory, trust me, by far. Anyway, I was going to bring the book and even show you, but it was too heavy. All right, so what we want to do is continue to make infinity a precise thing. We basically talked about some paradoxes in infinity, but let's make this a precise kind of definition. How do we do that? Remember how you count? You make a one-to-one correspondence with your fingers when you start out with the objects you're counting. So let's talk about sets of objects and compare the sizes of sets. So two sets are considered equal if they contain exactly the same elements. The set A, 2, 4, 6, is exactly the same as set B, which has 4, 2, 6. So we call those sets equal. We also call sets equivalent if there exists a one-to-one correspondence between the elements. In other words, they have the same number of elements, right? They're called equivalent. So if I have another set called C that had 1, 2, 3 in it, that will be equivalent to A and B because they have, although different elements, they have the same number of elements. Make sense? Easy peasy, right? Nothing is ever easy with infinity, though. So we call the size of a set its cardinality. Hence the cardinal numbers that Cantor said before. A and B are certainly equivalent, but C equals 1, 2, 3 is not equal, although it's equivalent. Everybody okay with that? Oh, it's equivalent, but not equal. Boy, I didn't get any sleep last night because I was thinking about infinity. Trust me, I really was. All right. So let's talk about some sets of numbers. We have some sets of numbers, the counting numbers called natural numbers, so we call it by n. It's all 1, 2, 3, 4, and on and on and on. It's an infinitely sized set. There's the set of all integers, basically all the counting numbers, plus 0, plus all the negative numbers, integers. Okay? And we use z in mathematics for that. Anybody know what z stands for? It's German. Zahlen means integer in German. And then we use I don't know what q stands for. Somebody just picked it. It looks like a good letter. But we use q for all those numbers that can be expressed as a fraction. A over b. It's called a rational number. Okay? And it turns out that the set of integers is in this, because b would just be equal to 1, and a could be in any one of those numbers up there, right? 2 divided by 1 is 2. 5 divided by 1 is 5, and so forth. And z is also in there, too, because of the exact same reason. Okay? So these can be all the negative integers and all the natural numbers. So, by definition, any number expressed as a fraction is a rational number. And any element which terminates or repeats may be made into a fraction. Okay, like 0.125 is what? Anybody know the fraction? 1/8. Very good. So forth, like that. Okay. Irrational numbers are exactly that. They're irrational. I almost wore my irrational integer shirt today, my irrational number shirt today, but I did not. They are all the decimal numbers that have decimal exponents that never repeat and never stop. They're infinite. Okay? So pi would be an irrational number. It never repeats any portion of its decimal number. Okay? And the irrational numbers, together with the rational, comprise a set called the real numbers. We have all kinds of other numbers out there you don't want to get into, complex, numbers they're called and so forth. But don't worry about them. We're just going to talk about these sets from now on. That's it. All right. Now, a set is finite if it is empty or if there's a natural number, n, such that it's equivalent to this set there. In other words, it has n elements, where n can be 0 or n can be a finite number. Right? It could be a Google, but it's still a finite number. Okay? A set is infinite if you cannot count it completely. Okay. George Cantor came along in basically the latter half of the 19th century and asked, are all infinite sets equivalent? I don't know why he would ask that question, but he did encounter some weird things in his mathematics. He basically invented set theory, okay, which is the foundation of all mathematics today. So in other words, can we get two infinite sets to always be in one-to-one correspondence with each other? So basically using your fingers and correspond to, say, just counting them all up. Okay? Or, in other words, do two infinite sets always have the same size or cardinality? To his surprise, we can't. And he did this. So he said, well, wait a minute. Let's take the natural numbers and see if we can count. It seems like we have all the natural numbers in the integers, right? But we have all these negative numbers in the integers too, right? All the negative natural numbers, and 0. It seems like there's twice as many of them, right? But it turns out there's the exact same number. Infinite. And how he did that was he set up this one-to-one correspondence. There's the natural numbers, and there's the negative numbers, but we're going to put them in this way. 0, 1, then negative 1. 2, then negative 2. Then 3, then negative 3. And he set up this one-to-one correspondence like this between the natural numbers and the set of integers. And you can formalize this by this formula here. For every natural number is paired, every even number is paired with 1/2 of that number, and every odd number is paired with 1 minus that number divided by 2. Okay, so it's 1 minus 3 divided by 2 is negative 1. 1 minus 5 divided by 2 is negative 2, and so forth. And with this pairing, there's a one-to-one correspondence. You can prove that the size of the natural numbers is equivalent to the size of integers, even though it seems like there's twice as many. But he even went on. He said, well, I'm successful with that. Maybe I'll do something even more impressive. Maybe I'll make a one-to-one correspondence to the natural numbers to all the set of irrational numbers, all the fractions. Oh, my God. Seems like there are a lot more fractions than there are natural numbers, right? Well, let's do that. You can even do this too. And I'll even show you what he did. This is a famous argument in all of mathematics called the diagonal argument. Okay? So he made this one-to-one correspondence between natural numbers and fractions. And he made this diagonal argument. I'm not going to get into the details, but in other words, you can make this one-to-one correspondence, which means that the size of the natural numbers and the size of the set of all fractions is exactly the same. Cardinalities are the same. There's a lot more fractions, though, don't you think? It seems that way. But then Cantor said, well, let's go crazy. Let's talk about those real numbers, which are all rational and irrational numbers. Well, he did this. He said, okay, well, first of all, let me back up. Everything that can be put into correspondence with natural numbers is called a countable set, because natural numbers are what we count with. So he mentioned the countable term before. So it's a countable set. If it's not equivalent to n, the natural numbers, is called uncountable. He found that the natural numbers is not equivalent to r. Remember, equivalent means the size. So in other words, the cardinality of r, the real numbers, all the rational and irrational numbers, is not the same as all the natural numbers. You would think there's an infinite number of real numbers, there's an infinite number of natural numbers, you could find a correspondence. But you can't. And he proved it. He found that r was uncountable. And basically, he just concentrated on that little interval between 0 and 1, not including the endpoints. And he showed that there are more numbers, more real numbers, between 0 and 1 than there are infinite counting numbers. How is that possible? He showed it. He did this with a proof by contradiction. He said, assume it's equivalent, then there must be a one-to-one correspondence. And he tried to find one, and he proved that there cannot be found. A correspondence cannot be found. I even showed it to you. It's very easy. Watch this. He basically said, okay, assume there's a correspondence between all the natural numbers here and all these never-ending decimals, right? Assume there is one. Well, he said, I can always find one that's not in my list. All I do is this. I say, okay, here's my thing here, and I take the first one of the first number I'm listing, the second decimal of the second number I'm listing, the third decimal and the fourth decimal, and what I'll do is that if it's, say, this is one possible thing you can say, if it's, say, the ith digit is not a 1 or a 2, then you can call it a 1 or a 2 if you want, but basically make it a different number. This is also one of those diagonal arguments. Make it a different number that's in the parentheses here, and that number that you create will not be anywhere on that list. In other words, there's no one-to-one correspondence. Now, here's the interesting thing. Cantor proved this in 88 or somewhere around there. Today, you will find people out there on the internet, on the webs, that say that this is impossible. The real numbers have to be countable. And they will show you a proof that their answer is right. It's wrong. We in the mathematics community call them Cantor cranks. Don't be one of them. Trust me. They're not fun to deal with. They're like a Republican. Ooh, did I say it? Didn't mean to bring politics into the program here. All right. So we can generate a new number, however we want to do it. That's not on the list. That's different from everywhere in that original correspondence. So since it's not part of that proposed correspondence, there is no correspondence. And you get a contradiction in your proof. So n is not equivalent to r. But that's the weird question. What the hell does that mean? We have an infinite number of natural numbers. How many real numbers do we have then? If you said infinite, you might be right, but you might be wrong. Which one is it? It turns out that because the cardinality of the real numbers is greater than the size of the natural numbers, there's a number bigger than infinity. And this is where it really becomes interesting. What do you mean bigger than infinity? And I always usually ask, when I ask questions in my class, I always include myself at the end of the question. What do you mean bigger than infinity, Dr. Tom? Well, let me answer that question. turns out that all the sets that are countable, the little lazy 8 that you call infinity, Cantor invented another symbol for it. He called it aleph null. The null just means a 0 subscript there. Those are called countably infinite. That's the size of the natural numbers. He also invented this thing saying, well, the collection of all sets equivalent to the real numbers have a cardinality called C, which he stands for the continuum. Not like natural numbers, which are discrete. He called it the continuum. And they are uncountably infinite. That was his words, his language. So real numbers can be shown to be in a one-to-one correspondence with a point on a number line. Turns out with a point on a plane as well when you increase the dimensions. It's also the same number, uncountably infinite. What about other sides of infinity? Cantor went on. This is the definition of persistence. Crazy or not, he went on. He said, well, are there other sides of infinities? He showed that there were an infinite number of sizes of infinity. If your mind hasn't been blown by now, you might as well leave. Okay? He invented these symbols. He just gave them different subscripts. Aleph 1 stood for the next size infinity. Aleph 2 was the next size, and so forth. And it turns out there's an infinite number of these alephs. It gets even worse. I can't even begin to describe to you how worse it gets. I mean, right now, there are set theorists out there that all they do is study what's called large cardinal numbers. And when I say large cardinal, I mean large infinities. And there's an arithmetic associated with these. There's an algebra associated with these. And it is crazy. I thought, I'll buy the book, and look at the first couple pages. I couldn't even understand page 2 of this. Well, Hilbert didn't believe any of this stuff at first, but after a while, he decided, maybe this is really cool stuff. And he had this famous quote, from the paradise created for us by Cantor, no one will drive us out, not even the Cantor cranks. However, just as a side note, George Cantor ended up dying penniless in an insane asylum. When he was publishing these results, one of his mentors, Leopold Kronecker, doubted his theories. And Kronecker was a strange fellow. He was a mathematician, but he basically ad hominem attacked Cantor all the time, called him names, called him a buffoon. I mean, not names that we would call each other these days, but the civil calling names back then, buffoon, how can you be this crazy, and so forth, and wouldn't stop with the name calling, which led Cantor to just kind of go crazy. Most mathematicians didn't actually accept his work either, but he maintained it was the case. And the William Blake poet, kind of symbolized eternity in this quote here. I won't read it for you because that's something that you probably all have heard already, so it's a nice way to talk about infinity. One other topic, though, that came out was when Cantor was still non-crazy, he would talk about something called the Continuum Hypothesis. Remember that C, the cardinality of all the real numbers? He said, where does that fit into that scheme of all those alephs, those crazy infinities that he had? Well, he knew that it was larger than that first infinity, right? Larger than the natural numbers. But was it larger than the second uncountable, or the first uncountable infinity, Aleph 1? He was never able to prove that C is equal to Aleph 1. Also kind of leading him to the insane asylum. So was there an infinity between the regular old infinity that we know and the infinity of the real numbers? He couldn't prove it. It's called the Continuum Hypothesis. There's a generalized Continuum Hypothesis as well, but we won't talk about that. But one of the most famous logicians of the 20th century, Kurt Gödel, he could prove that the Continuum Hypothesis was consistent with the axioms of set theory. It will not lead to any contradictions. He couldn't prove it true, he just said it was consistent. The weird thing is that another logician, Paul Cohen in 1963, he could prove it, assuming the hypothesis was false without any contradictions. So which is it? Is it true or false? We still don't know. This is really weird. We still don't know. Paul Cohen's still alive, I think. So So we can never prove it true or false within the axioms of set theory that we have now. So that's a whole other ballgame there. It's called Gödel's incompleteness theorems and so forth. But anyway. So the last quote I have here is from Buzz. Young man, in mathematics, you don't understand things. You just get used to them. You just might not understand these, but the more you hear about it, the more you get used to it. And you're like, all right, whatever. There are different sides of infinity. Woo. Actually, it wasn't Buzz Lightyear who said that. It was John von Neumann. Not the John Neumann back there, but a different one, a mathematician. So we really get used to the ideas of infinity. So if you are interested in looking at some of these ideas yourselves, I've given you some references here if you want to. Check out the video and look at some of these references. I recommend the first one here, and I recommend the last one. This is the latest book that I found that was published by a popular author. This is one of the first ones, but it talks about the cultural history of infinity, like a lot of the artists and all that kind of stuff I talked about earlier. If you really want technical accounts, you can look at this stuff here. I would say, by the way, don't read Rudy Rucker. That's very technical. I just read it like 2 weeks ago. Wow, this is really technical. And, of course, there's a biography of George Cantor if you really want to know what happened to him. I believe that's all I have for today. I hope I blew your minds. I hope that Woody and Buzz now think I'm crazy. I hope you don't think I'm crazy, but this is a fact of mathematics that we just have to live with now. It's the way it is. So thank you very much.
All right. Thank you, Tom. So as always, you're open to some Q&A, right?
Yes, I'm open to Q&A.
Great.
I might not be able to answer your questions, but...
Yeah, just two rules. Hold this towards you. So for the benefit of the video, we need to pick it up. Hold it close, hold it towards you, and hang on to it in case there's some back and forth. Otherwise, we'll miss the dialogue. So who has a question for Tom? All right.
I have what I think are two related questions, and if you could answer them both.
I hope.
At the end of the second one.
Okay.
So actually, you kind of answered one of them, maybe, when you brought up the idea of different sizes of infinity. Okay. So here's the first question. Can you have variable infinities? And do you envision, a lot of times during your talk, you brought up the idea of this is weird, this is weird, this is really weird, that's weird, this is weird.
Yes.
Do you envision weird theories being infinite?
Okay, so the first question about variable infinity.
Yes.
Now, don't laugh. I'll tell you why. So the first question, variable infinities, I don't know. I don't think that they are necessarily cardinality is a variable per se. I don't know, though, about that one. I've never heard that before. So in all my readings of all these things, I've never heard that. So I'm not really sure, but I think my answer is probably not.
Okay.
Okay?
Okay.
As for the second, are there infinite theories of infinity, essentially?
Do you envision weird theories being infinite?
There are.
You know, you may have presented 10 or 20 here, or something,
Yeah.
or 30.
Yeah.
Well, that's not infinity to me.
That's right. It's not. But interestingly enough, if you may think that's a strange question, it really isn't. If you read Rudy Rucker's book, you can find that there are certain mathematical branches that have infinite theorems of infinity. And it goes on from there. And you can prove that there are infinite theorems. It's really strange. There are both. There are countably and uncountably infinite ones, actually. That's where I started losing it in the Rucker book. Where I was like, what? Okay. So I didn't really understand all that, but that question actually has an answer.
So Rudy Rucker has a book and he discusses this thing.
Yeah, it's called Infinity in the Mind.
Infinity and the Mind. Okay.
Yep.
Yeah, thank you.
Sure.
All right, we'll come over here to Dave.
Don't you think that I don't know whether it's practicality. Don't you think that the practicality of mathematics is more significant than the theory? And that's really physics. And, you know, how many of these things that we just talked about have practical applications to black holes and things that are practical reality?
That's a good question. So when I mentioned this, that I was giving this talk to my wife, she basically said, well, that's crazy. Don't you want to listen to my, at least see my slides? No. She's a physicist as well. And as my training as a physicist, it's kind of like applied mathematics, you're right. I'm a theoretical physicist by training. There are instances of weird math, becoming more useful later on. Cryptography and number theory, for example. Back in the early 20th century, G.H. Hardy, a prominent number theorist, wrote, number theory is a pure math. It will never be applied. Now we can't live without it, with cryptography and security of transactions on the internet and so forth, right? So I won't say this will never have any applications. As far as I know, though, this is very abstract math. I don't know of any other applications beyond what I've talked about in terms of like something in physics, maybe the only singularity of the black hole, or when we get down to the quantum levels, where does infinity arise? Infinity does arise in physics in terms of number of ways that you can calculate certain quantities, but you get rid of them. Why is that? Why does that happen? Why does that work? Nobody knows. Maybe something like this would help answer that. I don't know. But beyond all these infinities, I don't see a practical application for it, no.
Which brings me back to my answer to your first question.
Oh, okay.
Things that we cannot know.
That's probably a good, accurate description then. Yeah, that's right. I like that.
Okay, who else has a question for Tom? All right, Donna.
I want to apologize for arriving late,
Oh, that's okay.
but also I'm glad I arrived late because I have very low understanding of mathematics. I have felt bad about myself, infinitely bad about myself, and my lack of knowledge. But I think through your talk, now I can say I feel twice as infinitely bad about my lack of knowledge. So I did learn something today.
That's in itself a paradox. I love it.
Is it?
I can address that. But
Possibly.
you need to put the focus on everybody else here who now is in the same boat as you, so we're all on the same plane. It's actually a good thing at the end of the day. So there's as much as the person in the world who knows the most knows as little as the rest of us, if there's
It
that
seems
much
that
else
way,
out
yeah.
there.
Yeah, that's
So-
a good paradox. I like it. Yeah, yeah. Very good. And to kind of add to that, so there are different types of numbers out there. I talked about cardinal numbers that measure the size. Well, there are ordinal numbers as well. They talk about the order of things, ordinal, right? And it turns out there's an ordinal infinity that's different from cardinal infinities. I know, it gets weirder. Ordinal arithmetic is really strange. The ordinal number for infinity is a Greek letter called omega, looks like a W. But 1 plus W does not equal W plus 1. It gets weirder than that after that. But 2 times W is still W. Maybe now 3 times W, but that's still W. Omega. Any other questions?
All right, Martha.
This is just a little comment about whether any of this has to be practical. I don't think true mathematicians care whether it's practical or
Agreed.
not.
Agreed. I mean, mathematicians do math because they have to. It's a curiosity-driven field, just like mountain climbing. Why are you climbing Mount Everest? Because it's there, right? Because it's something that the human mind can now comprehend, or at least some mathematicians can comprehend this different sizes of infinity. And I think that's fascinating. I mean, this is why I'm giving you a talk on this, because now you know. You may not understand, but you know of this existence of different sizes of infinity. Go home and tell your daughters and sons and granddaughters and all that stuff. They might think you're crazy, but who cares? It's true. Right? I think it's fascinating. My daughter thinks it's fascinating stuff too. That's why she wanted to write the quote. But, my wife's like, that's nonsense. There's only one side of infinity. But no, I can prove there's not. I don't want to see it. Okay, fine. But I think it's so cool that I wanted to tell you guys about it. I almost talked about black holes, by the way, something which I'm much more familiar with. But, I thought, no, I'd also like infinity. I've got a couple of talks on this already. One's much more mathematical than this one. Oh, yeah. It's for math majors. I prove everything I talk about, everything. And but this one was the, kind of like the high-level view of things, but enough to give you a taste and a flavor of what kind of some mathematicians do. Not all mathematicians do this, of course. Mathematics, like any other branch, is very stratified, right? Different areas for different people. And these are, most people that study this stuff are set theorists. And set theorists, whew, they're out there. They're beyond infinity, as far as I'm concerned, themselves. So, any other questions?
Right here again, and then I'll come back.
I wanted to ask you this question. I don't know whether you consider yourself more a mathematician or a physicist or both or neither. The work that that Einstein did and the work that the other guy did is just escaping my mind. The guy who invented calculus, not Leibniz, the other guy.
Newton.
Newton, thank you. Do you consider, which of those two do you consider more revolutionary and more original?
Newton was definitely more original because he invented calculus. He also invented the 3 laws of motion and so forth, kind of, based on observations and so forth, and from Galileo, and that Einstein built upon that theory, built upon that structure. But he was also revolutionary in the way that he kind of went over and above what Newton did. So, in my mind, I think Newton was probably more the revolutionary at the time, but Einstein basically overcame that with more and more, kind of things to do.
So that's kind of a temporal, not examination, a temporal adjustment. I mean, why would somebody who comes later have to be less revolutionary than actually the guy? Would Einstein have been able to figure things out with Newton? Is that too much of a mind projection?
No, I don't think so. Einstein was very smart, and I think he might have been able to figure it out had he been in Newton's time as well. So, I think that there's just different times. You're right. It's just a temporal distance there.
I think there's an argument or a polemic about whether Leibniz actually should be credited with inventing calculus.
Yeah, that's all.
Is that right?
Yeah.
Is that right?
Yeah.
I've
They
heard
had
that.
arguments back in the day. They hated each other and so forth, and each one wanted the credit. So Newton actually gets the credit because they actually invented the stuff before Leibniz did, but they both published about the same time. The weird thing was that Newton did all that 20 years before and didn't publish.
Right.
So they
and then there was an argument about Leibniz maybe hearing about what Newton did, and that was a back and forth kind of
Yeah,
thing.
there's still back and forth, I guess. I don't know. But I think that we've kind of come to a consensus. And I consider myself more of a physicist, by the way. But I like to study mathematical physics. And the math I like to study really, not this stuff. This is kind of like a hobby. I usually like to study for my work differential geometry, which is the calculus on surfaces.
Okay, we're going to take one last question, and then we've got something special for those who don't mind staying, which we'll get to in 1 minute.
So I think my question has already kind of been touched upon in terms of the practicality of understanding this. So when I think of when we understood E equals MC squared and how that revolutionized other technologies and created new technologies, I wonder if you ever fantasize about us understanding this really deeply and how that could affect technology and our future progression in that regard.
I do fantasize about that, partly why I was awake all night last night. And some of the weird things that have been kind of suggested for these to make this semi-practical, if you want to call it that. There is a theory out there that in physics called the multiverse theory that some of you may have heard of by popular accounts and so forth. It's really taken seriously by a large number of physicists, especially those who study string theory. There are infinite number of universes out there that are very similar to our own, maybe with different laws of physics or whatever, right? But what kind of infinite is it? What kind of infinity is it? Is it countable infinity? Is it uncountable infinity? And it turns out, Rudy Rucker, Infinity of the Mind, goes into this a little bit, and it gets crazier with it. He calls it the mindscape, which is an infinite of infinite of there is he calls it the absolute infinite. And that's how many universes he thinks there is out there. Not just infinite, not just countable infinite, not aleph 1, not aleph, sub-aleph, whatever. It's the absolute infinite. And he says in the book that you can equate that to whatever you like. You can equate that to God if you really wanted to, or whatever you want to call it, the one, like Neo, the one, right? But nobody really knows. I envision that hopefully maybe someday we might be able to figure that out. Somebody may come along and say, that's a bunch of hogwash. Somebody may come along and say, hey, maybe we can actually prove that this is true. I have my doubts about the latter. I have higher hopes for the former because it doesn't seem right, but you never know. So I have an open mind about some of these things, but I just want to be forewarned. If somebody did say, you can, and probably you guys are familiar with this, you should have an open mind, but not so open your brains fall out. Okay, so there's a certain thing, but I would definitely not encourage you to not ask questions. Double negative there. Ask questions all the time, man. Keep going. That's what Cantor did. Of course, he did end up in an insane asylum. But regardless of that, still, you should ask questions.
And on that note, thank you so much, Tom.
Thank you again. Thank you, Jason, for having me.